So when we left off, we talked about a type of proof called a tabular proof. So what a tabular proof is again, we draw a table on both sides. So however many variables we have, we draw it on both sides, and we compare the two tables to see if they're equal. If all of the cases are aligned, so for every single case, the output is exactly the same, then the two statements are logically equivalent. Otherwise, they're not logically equivalent. So you could, as you could probably imagine, there are many different expressions that are logically equal to each other that only make sense. But there are a set of laws which we can also use in order to prove that two sides are equal or two expressions are equal. So if you take a look at this table, the law that is at the very bottom here called implication reduction. So I didn't have enough room to write it, but this is implication reduction. Um, X implies Y is logically equivalent. Now, I used equal signs here, but you can imagine every equal sign that I have is actually a logically equal to. So just because I couldn't type it up on my computer. X implies Y is the same as not X or Y. So they are logically equal. And please look back at the previous example to see why that is. We drew a table for both sides and we compared it and we saw that they are equal. Now, there are other laws here that we can also look at. So I'm going to start with the identity law. So all of these laws actually come straight from the definition of the and or the or. So for example, if we take a look at our definition for the or operation, um, the disjunction operation. We have the xy, so we have our four cases for our xy's, and for x or y, the table is defined as 0, 1, 1, 1. And again, please remember this for the time of the quizzes or exams. This is going to help you a lot if we know the definition according to the table. Now, if you take a look at the first identity law, if you take a look at this one right here, this is stating that when I OR an X with something that is false, okay, so an expression that is always false, it is equal to X. Now, what are we saying here? Well, it essentially in the table, we're saying that Y is never true, is never equal to 1. So it's always equal to 0. It's always false. So we're going to strike out this column, or sorry, this row and also this row. So where the y's are ones, I'm not looking at those situations in this case. And what you're seeing is that the outcome, the x or y, is exactly equal to x, right? So you can probably see where that law is coming from. You could probably reason it out as well. So if I said today is Thursday, or 1 plus 1 is 3, right? So 1 plus 1 is 3 is always false. So the truthfulness of that expression is always dependent on whether or not it's Thursday, right? So it's the same as saying today is Thursday. Okay, so again, uh, try to convince yourself of that. The next one we can look at is this next law called domination. So this law, this domination law, is again using an or operation, but this time we are oring something that is always true. So again, I'm going to strike out this row and this row, right? Because again, the y's do not matter. Sorry, the y's cannot be false in this case. We're taking the x and oring it with something that is always true, and what you're seeing in the output is that it's always equal to 1, so it's always true. So again, we're pretty satisfied with this. So this is where that law comes from. And again, we can reason that out. If we said, today is Thursday, or 1 plus 1 is 2, then that statement is always true, right? Because 1 plus 1 is equal to 2 is always a true statement. So that is dominates the X. Okay, on the other hand, if we take a look at the and operations, we can take a look at and here. Okay, so let's take a look at this one, and let's go to the and definition. So if we have x and y, and the and operation, sorry, goes like this: 0, 0, 0, 1. Okay, so again, the definition of and is both inputs have to be equal to 1, and then the output is equal to 1. Otherwise, it's equal to 0. So in this case, what are we saying? This case, we're saying this is the idempotent law. This is saying x and x is equal to x. So if whatever x is, if we're anding it with the same value, then the outcome is just x. So if we take a look at, so here you see x and y are not equal. So I strike this part out. X and y are not equal. So I strike this part out. So what you see is that it's exactly equal to x, right? So the outcome is exactly equal to x. And of course, I can go on and on, right? I can go on and on about this, but I'm just going to give you kind of some insight as to where these laws are coming from. So first, so the next one, we have a double negation. If I said not x, it's the same as x. So if I said it is not the case that today is Thursday, then it's really just, let's repeat that. If I said it is not the case that today is not Thursday, then it's the same as saying today is Thursday, right? If I said it is not the case that today is not Thursday, then it's the same as saying today is Thursday. So that's a double negation law. We also have a complement law that says if I have X or not X, that's true. That's always equal to true. And if we have X and not X, that is always equal to false. And we did an example of that before. So that's called the complement law. We have the commutative law that says if I'm using the or and, it doesn't matter the positioning, right? So X or Y is the same as saying Y or X, and vice versa, and the same for and as well. Now, the next three are a little bit special. The associative, the distributive, and the De Morgan's law are all laws that we can expand, are generalizable. So what do I mean by generalizable? Well, first, let me go through the definition of each one, and then I'll talk about what the generalization is. So the associative says that if I'm using the same operation, the or operation, it doesn't matter where I put the bracket. The logic is exactly the same. In fact, I said earlier in an example that if we're using the same operations, I can take away the brackets altogether, right? So I don't need the brackets, in fact, if I'm using the same operation. Distributive law says I can distribute a variable inside of a bracket, much like how we do FOIL in math, right? Well, not really FOIL, but distributing in math. FOIL actually does work here as well. So that is an extension of this rule. But distributive says x and y, and then I also have x and z. So we have x and y or x and z. So it's kind of like I'm distributing the x inside of this bracket. Okay, and it works the same for x or y and z as well. So the key here to note is that this operation is the opposite of the inner operation. Now notice, we are really only working with ands and ors here, right? So we're not really looking at implications, nor are we looking at biconditionals at this point. We will later on in this section, but these laws are really only pertaining to ands and ors, and you're going to see why in 1 second. So that's the distributive law. So it's like distribution in mathematics. And then finally, we have the De Morgan's law. So let's imagine that we have x or y, and then inside this x or y bracket, outside of this x or y bracket, we have a negation. So we have negation x or y. We can distribute the negation inside. Again, very similar to mathematics, but when we distribute the negation inside this bracket, this or becomes an and. Okay, so that is the rule. When we distribute the negation inside the bracket, if it's an or, it becomes an and then if it's an and, it will become an or. So the negation ends up next to the individual variables. Okay, so these are just patterns that I've explained. So all of these laws are really just patterns. And the point of applying these laws is to be able to look for these patterns and to apply them accordingly. Okay, so that's our goal in any question that involves algebraic proofs, that we're using these laws of logic. And these are called algebraic proofs. Now, earlier I mentioned that these three laws, associative, distributive, and De Morgan's law, are expandable or generalizable. And what I mean by that is the concept can be generalized. So for example, associative, I can have something like x1 or x2 or x3 or all the way up to or xn. And the same principle goes. The bracket can go anywhere, and the logic is exactly the same. Okay, so this is expandable. This idea is expandable. Same with distributive law. So if I had x and then we had a bunch of variables in here. So x2 or x3 or x4 dot dot dot, right? I can distribute the x inside of the bracket no matter what. And as I said before, FOIL also works in this case, right? So the idea of the idea of FOIL also works. So just to give you an idea what I mean by that, let's take a situation where I had x or w, and then and y or z. So let's say we had something like this. We can do x and y, x and z, w and y, w and z, and all of these are going to be ORed together. Sorry, I ran out of room there, but I hope you can see what I'm writing. All right, so we can still apply something like FOIL to distributive law. This is an extension of the distributive law, and that's what I mean by those three laws are generalizable. And once again, for De Morgan's, it also is generalizable. So if I had X or Y or W or whatever, I can still distribute this negation inside with the same concept. Okay. So we will actually see some application of this a little bit later. But for now, let's do a very quick application. When would we use something like the laws of logic in the form of a proof? Okay, so let's take a look at this example. So it says show algebraically that x or not y and y is logically equal to x and y. Now, the word algebraically here means that I want to use algebra, meaning I want to use the laws of logic in order to make this proof. Now, typically, what I would do in this type of situation is I would try to simplify. It's always easier to simplify. So I take the more complex side, which in this case is the left-hand side. So the left-hand side is more complex here. And I want to simplify it to the right-hand side, which is less complex, which is more simple. So so whenever we want to simplify, whenever we do simplification, this is a very nice application of using laws of logic, right? Using algebra. Okay, so one other thing that we should note is that whenever I can put a bracket around some expression, so for example, I see here that I have a bracket around this part right here, but I can also put a bracket around the not y. And anytime I can put a bracket, I can theoretically put a bracket around some of these terms, I can do that and I can substitute it as something. So for example, I can take this whole bracket and I can substitute an A in there. Okay, this is called the substitution law as explained in your textbook. So if you ever see any textbooks say, you know, this is the substitution law, that's all we mean. Whenever we have a bracket and I replace that bracket with some variable, right, a or whatever, this is called a substitution rule. So keep this in mind because that's going to be very important. I'm going to think along those lines. So right now, what I'm going to do first is I'm going to start with the left-hand side. The left-hand side, if I apply the commutative law, so the commutative law, I'm going to say y and x or y and not y. So what I did there is I imagined that this bracket was an A. So I have A and Y, right? So I have A and Y, and I could swap that and I can have Y and A. And that was called the commutative law. So that one right here. Okay. So that was from substitution, right? So I have A and Y, and I can switch the position of the two. Okay. Now we can do a distribution law. So I can do Y and distribute it into this bracket. I can do Y and X or Y and not Y. So this is the distribution law. Now again, I want to point out that I did use substitution here. It's because if you imagine the not y, right? So if you imagine not y is actually one term, right? So I can put a bracket around that. I can call it a, right? So this becomes y and x or a, and then I just applied the distribution from there. Although I hope you can see without physically changing the substitution, we can just write it out like this. Okay, so the next thing we can do is now I want to point out that the complement law. The complement law is very useful because anytime we have a variable and the opposite of that variable. Now, what I mean by this is y and not y, for example, right? So I have a variable and then I have the opposite of that variable, negation of that variable. I can either simplify this to true or false. I do a pretty nice simplification here. So according to the complement law over here, that y and not y is going to give me a false. So here I have y and x or false. And that was from the complement law. Okay, next, if I imagine this y and x to be one term, this bracket to be one term, let's call it A, we have A or false. Okay, A or false is going to give me, according to identity, it's going to give me, well, A. So which means I am left with x and y. So this is from the identity law. So again, imagine this bracket y and x as one term. So we have A or false is going to give me A, right? Okay, the final thing I need to do is this, I need to match the right-hand side. So I'm just going to turn this into x and y, which is from the commutative law. So the commutative says I can switch the order of the two. And now I find that the right-hand side is equal to the left-hand side. Now I should point out that every step that I took here from the from the left-hand side, I had equal, 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 equal. So these are all logically equal. So I find that ultimately that the left-hand side is logically equal to the right-hand side. And that's how I can show that these two are logically equal to each other. Okay. All right. So there are a lot of practice questions in the textbook. So I highly recommend that you go into the textbook and try out some of these algebraic proofs, the proofs involving the laws of logic. So they're going to help you a lot. So just understanding how to use the proof, how to use the laws, when to use the laws, and in this situation, what strategy should I use for simplifying and everything like that. It really just takes practice. So just like any other mathematics course, it just takes practice and to be able to train your eyes to see, oh, in this situation, I should apply this law and then this will simplify. Right. So this, you should start training yourself to think along those lines. And we're going to do some of that in the in class as well. Okay. So uh, so the other thing I wanted to say about algebraic proofs versus tabular proofs is that what is the difference, and when should I use a table versus when should I use algebra? And the short answer is I will typically tell you, but in the case that I don't tell you, like on a quiz or on an exam or something like that, um, I would typically point to or hint at what you should use. So, for example, if I just said, is A logically equal to B? So, if I just gave you this statement, is the left hand side equal to the right hand side in this case? Well, what you should do if I said, is it equal? Right. So, meaning that I don't know, it could be false, it could be that they're not equal. So, in such a case, I should use a table. Okay. So, in those cases, I should use a table because on the chance that the left hand side is not equal to the right hand side, algebra is never going to tell me that. Okay, so once again, the disadvantage of using algebra is that if the two expressions are not equal, algebra is never going to tell me. Right, so I can apply laws all the way along, but if they're not equal, then algebra is never going to tell me that. So I can never use algebra to say that these two are not equal. Okay, so just keep that in mind. I cannot use algebra to say that these two are not equal. So I can't do that. Okay, another difference between the two is if I said, on the other hand, if I just gave you the expression x or not y and y, so if I just gave you this expression and the directions were simplify, Now we're going to do an example of simplify in the next example, but simplify typically means that for every variable, I want the least amount of them, right? So you see here, I have two y's and I have one x. Can I simplify it? Can I make it less, right? So can I make it less than 1x? Can I make it less than 2y's? So that's what simplify means. And so if the directions were just simplify, well, I can't use a table to do that. So the disadvantage of using a table is that I cannot simplify an expression. Okay, so to simplify an expression, the only way to do this is to use algebra, is to use algebraic laws in order to do that. Okay, so just remember those two things. And then if a question like this comes on a quiz, then you know which one you're going to be using. But as I said, a lot of times I will tell you exactly which method to use. Okay, so let's take a look at our table in a little bit more detail. So you notice that this table actually has two columns, right? For most laws, there's actually two versions of the same law. So what's up with that? Well, why is it that there for identity there are two identity laws? Well, this comes all the way back, if you remember, in the first video that we talked about in this section, we were defining the difference between a conjunction and a disjunction, right? So what's the difference between conjunction and disjunction? And well, the definitions were actually very similar, right? So the only difference between disjunction and conjunction is that we swapped the true and false in their definitions. So what is the relationship between these two laws? Well, there's this thing called a dual. So, what a dual means is that we are defining a compound or a dual of a compound proposition, and the dual is kind of the replacement of the true and false, so the flipping of the true and false, and also flipping of the ands and ors. So, I'll give you a quick example. If I had an expression called S, and this S is P and Q or not S, okay? We'll say or, well, actually, P and true. Let's say P and true and or not S. Now, I understand that this is not the simplified expression, but I just wanted to prove a point here. So the dual of this expression is going to be signified by S and then D, is the flipping of the ands and ors as well as the true and falses. So the dual of this is P or, so you see we had an and now it's or, false, we had a true and now it's false. And then now I have an and, not S. Now notice that the nots don't play a role in the dual. Okay. And so there should be a bracket here. So this is the dual of the top expression. And if you take a look again, if we take the dual of the bottom expression, we will again get the top expression. So these are kind of like inverses of each other, right? So applying this dual is like the inverse of each other. So you might be asking, what's the point of having the dual? Well, firstly, I should point out that if I just take an expression and I apply the dual to it, it tells me nothing. Okay, so if I take an expression, find the dual, it tells me nothing. They're not equal. They're not related in any way. I can't predict what the table is going to look like. They give me no extra information. However, if I find, so if you take a look at this principle of duality, if I find that I have two expressions, S and R, that are logically equivalent to each other, then their duals are also logically equivalent to each other. Okay, so I'll say that again. If I have two expressions, S and R, that are equal, that are logically equal to each other, then their duals are also logically equal to each other. And that's a law. Now, there's a proof for it, which I'm not going to go through here, but you just have to trust me that anytime I find that two expressions are equal, immediately I know that the duals of the two are also equal to each other. So how can we apply this? Well, take a look at this situation. So if I take a look at complement, for example, if I know already that x or not x is equal to true, okay, x or not x is logically equivalent to true, then right away I know that x or not x is equivalent to false because these are duals of each other. Okay, So vice versa is also true. If I know the left-hand side, sorry, the right-hand side to be true, I know the left-hand side to be true. I also, because they are duals of each other. Now you'll notice that there are rules like double negation and implication reduction that don't have duals. In fact, the duals are themselves. So those are ones that don't have two versions of the laws. But for most of these laws that you're seeing here, there are duals of those laws. So just keep that in mind. Now, just an application of this, and I did label this as 219. So let's label this example as 219. Since this since this proof here proved that this expression, the right hand side is logically equal to the left hand side, I can immediately say from the duality principle. So from duality, I can immediately say that x and not y or y is logically equivalent to x or y. So you notice that this is the dual of what we had up there. And we don't even need to prove this, right? So if we prove one, then immediately the other one is also true. And what you'll find is that if I try to prove the bottom expression, so if I try to prove this expression right here, I can use the exact same steps that I listed here, except I'm using the dual versions of those laws. So that's how they're related to each other. Okay, so remember how I said ands and ors only differ in true and false, right? In the true and false, this is how they're related, because it turns out that the conjunction and disjunction are actually duals of each other. And that's how this logic works. Okay, so let me repeat that one more time. If I wanted to prove this expression down here to be true, I can use the exact same laws in the exact same order, except I am using the duals of each of those laws. And this is what we have to understand about the laws of logic. Okay, so now I want to do one last example just to kind of end off this video, and maybe we can do a little bit more kind of in-class example at the end of this. So there is an application called switching networks. So here is how the application goes. So let's imagine that I have two locations. Let's call it T1 and T2. So I have two locations, T1 and T2. And let's imagine that we're going through a network that kind of looks like this. We have P, we have Q, right? So we have those two, and then we also have P, and we also have not T, and let's say that we also have P, T, and R. Okay, so this is just a T, right? Okay, so the idea here is that imagine that these are switches. Okay, so all of these variables represent switches. So a switch could actually be in one of two positions. So each of these switches can be in the on position. So the on position is going to be like this. So it does allow whatever it is that to go through. So this is the on position. And we also have the off position. So the off position is like turning off the switch, which cuts off electricity or fluids or whatever that's going through this network. It will turn it off. So the question is it possible for me to transport something from T1 over to T2? Is there a a assignment of these variables so that I can get stuff from T1 over to T2? Okay, so now you can probably say that, well, yes, because there's a very obvious solution here, which is just to make P equal to 1. Right? If I make P equal to 1, that means I turn on the switch for P. So that means the fluids or electricity or whatever is going to go always through the P from T1 over to T2. Right? So you can see, hopefully, that as soon as I turn on P, that there will be flow from T1 over to T2. But on the other hand, what if P was 0? What if I know that P was already shut off? Is there another answer to this question? Well, I think there is. I can set Q to be a 1. I can set T to be a 0. Right? So if T is set to be 0, then that means this switch is actually on. and then I can make r to be equal to 1. So if I assign q is equal to 1, t is equal to 0, and r is equal to 1, once again, I can get from t1 over to t2 by walking over those corresponding switches. So I hope this application is clear. Okay. Now, the problem is that this network might be very complicated, right? So I might have a very complicated network, but what we can do is we can use logic to simplify it, and we can simplify it to an expression that if there is a way to get from t1 over to t2 in this new expression, then surely there would be a way to get it in the old expression. So this is what we're after. Okay, so let's see if I can turn this into a logical expression. So we're imagining that we're fluid or whatever, trying to get from T1 over to T2. Now, once we get to this point, I have a choice to make. I can either go to P or I can go to Q, right? So I can go up, which means I have to go through P, or I can go down, which means I have to go through Q. So that means in order to get through that first section, either P has to be a 1 or Q has to be a 1. Okay, so I hope everyone is with me there. So either P is equal to 1 or Q is equal to 1. Either one of those will allow me to advance to the next stage. Now, just to satisfy some of your curiosity, would this be an exclusive or would this be an inclusive or, like this disjunction? And the answer is it's disjunction, because I could just as easily flip both switches, right? So I can do an on switch for both P and Q, and that would be fine. So I think I have the right type of or here. Now, the next thing is that if I'm fluid or I'm going from T1 over to T2, I would have to go through this point as well. I would have to make a second choice at this stage. So we have P or not T. So this would be the choice. I'd go up, I would have to go through P. If I go down, I would have to go through not T. And then a third choice I have to make is over here, which is P or T or R. So so again, I have to make this choice. I have to go through one and the second and the third. So this is going to be an and operation. Okay. And this would be the expression. Now, I want you to take 1 second just to convince yourself that if I'm able to go from T1 over to T2, then that means there is a way that I can assign the variables so that this expression is true. Okay, so I'll say that again. There would be a way that all of the variables can be assigned something so that this expression is going to be true. So if there is a way to get from T1 over to T2. So what I want to do here is actually to simplify this expression. Okay, this is actually a pretty complicated expression. Now, I'm going to simplify this expression by saying equal. Okay, so logically equal. So I'm going to put a P or Q and I'm going to have another bracket here. Sorry, this is not T, and then another bracket T or R. There's 2 brackets closing it. Now, just for a second, please convince yourself, if I distribute P inside of this bracket, that I will get the top expression. Okay, so when I distribute P back into this bracket, I will get the top expression. So, so understand that that is the application of this rule. The distributive law allows me not only to be able to put a variable inside of a bracket, but it also allows me to be able to take it out, right? To factor out a common P. Okay, so the next thing that we have to see is that we have 2 ands here. And theoretically, what I can do is I can put another bracket here, right? So I can put a bracket right here, right? And this will be exactly the same logic. So the usefulness of doing this is now I can distribute the not t inside of the bracket. So for the purposes, so I kind of looked ahead a little bit. I saw the not t and t, and I need to get them together somehow. Right, so I'm going to distribute the not t inside. So the rest of this is going to remain the same. We're going to have a not t and t, or we're going to have a not t and R. And this was actually another distribution law. Okay, now I'm going to do two steps in one now. And as you get more familiar with this, you will actually be able to do this as well. So I have a T and not T. So this is going to become false. If you take a look at the chart that we had before, T and not T will give me a false. And then I have a false, or we'll call this X. Call this thing X. So false or X is just going to give me X. So the only thing that remains from this square bracket here is going to be not T. It's going to be not T and R. Okay, and we have Q and not T and R. Okay, so this I did in two steps. So once again, this bracket here happens to be false. And if we call this X, false or X is just X. So I did actually two steps there. The two steps were complement and identity laws. Okay, so I did those two laws together. And then I can find that the last step here is I have an and. I don't need a bracket for that case. So the final step I'm going to do is I'm going to take out that final bracket, and this is what we end up with. And this was just you can call this the commutative law, right? But I'm just really taking the brackets away. Now, what we find in this example is that if I have T1 and T2 like this, then this is equivalent to drawing something like P. So you have P, right? So either go through P or go through Q and not T and R. Okay, so I hope you can see how I translated that. So once again, this expression says P or Q and not T or R. So this is how we can expand those two. And now we can say that if there is a way to make a true from this expression, then there's also a way to make a true from the top expression. So if there's a way to make the number two expression to be true, then there is also a way to make the number one expression to be true, an assignment of variables to make it true. Right? And we did actually say this from the beginning. We could make p equal to 1, or we can make q equal to 1, t equal to 0, and r equal to 1. Right? So I hope you can see the application here. So this is just an exercise in simplification. And there are, again, there are a lot of uh, uh, questions in the textbook that will require you to simplify expressions. Okay, so the last thing I want to do here is a very quick class exercise before we jump into our in-class assignments, I guess, here. So what I want you to do is practice this. So show that this expression is its tautology. And the second part is I want to prove using a truth table. So we'll do both of these together. Right now, you can probably pause the video and try it. But let's do them together now. So, so since we're using a truth table for the second question, for the first question, I think maybe let's try to use algebra. Okay, so let's use algebra for the first question. So, so now it doesn't say anywhere that we have to use algebra. So for the first question, we could just as easily use a table. And if you did, that would be fine. But let's use algebra here. Now I noticed that there is a there is a implication here. There's an implies there. So the first thing I'm going to do is turn those implies into ors and ands, because that's really the only way that we can work with those expressions. So I'm going to do a not p or, and then you can imagine the square bracket to be x, right? So not p or, we'll call it x. Okay. And then I'm going to turn this arrow in the same way. So I'm going to have a not p or, and then not q or, p and q. Okay, and now we're ready to go. Now, the first thing I want to do here is I see a not q and q. I want to distribute this inside of this bracket. So in this bracket, what I'm going to get is not q or p and not q or q. And we have a not p or and then that. Okay, so again, you'll notice that this part is a true. So this is a true. So Q or not Q turns out to be true. True and X is just X. So what we're left with in this situation is we have not P or, and then not Q or P. Okay, now again, we notice that we have an or and an or here. I'm going to take away both of these brackets because they're no longer needed. And now I can realign some of these variables. I can say P, not P, or not Q. So I've just shuffled these variables, and we can do that because we're using the same or. Remember earlier I said if we have P or Q or R, it doesn't matter what order we put them in. Now, in particular, I want you to notice that this part right here, P or not P, becomes true, and true or, and let's call this X, true or X is just equal to true. Okay, so ultimately, we've shown that this expression simplifies to true. So it's true. So it's a tautology. Okay, now again, I should have probably redefined the word tautology, but if you remember in our classes, the word tautology means that it's an expression that is always true. We wanted to show that this expression is always true. Okay, now let's take a look at the second part here. And if I can just grab, well, maybe I can do a straight line here. Okay, so I have this, and then I have P, Q, and R. So I'm going to draw a truth table for both sides, and I'm going to see if they match. So once again, the technique here is I have four zeros and 4 ones. And then I'm going to do 2 zeros and 2 ones, 2 zeros and 2 ones. And then I'm going to do 0, 1, 0, 1, 0, 1, 0, 1. Okay. So just for readability, I'm going to put another line here. And now I'm going to go through each one of them. I'm going to go through quicker this time, and you should verify my work. You should do this on your own as well. But let's take a look at Q and R. So Q and R is going to be equal to 1 when both Q and R are 1 and 0 otherwise. So it's going to be a 1 here and a 1 here, and then 0 everywhere else. Okay. So then we have a P. So I'm just going to copy down the P. Okay, I'm going to copy down the P, and then the implies is 0, 0, 0, right? So remember, the only case that the implies is false is if we have the 0, is if we have 1 implies 0. So these cases are false. Everything else is going to be true. And so this is our final situation. So I'm going to specify that this is the final outcome that I get from the truth table. And now let's verify that the left-hand side is also equal to the right-hand side. Now, again, we're going to kind of go a little bit faster here. P implies Q is only false when P is equal to 1 and Q is equal to 0. So P is equal to 1 and Q is equal to 0. Okay, I'm going to put those ones, and then P implies R is only going to be false when P is equal to 1 and R is equal to 0. Okay, and now we can take the AND operation of the two. So AND means that it is equal to 1 when both sides are equal to 1. So taking the AND, I get 1, 1, 1, 1. And then this is also a 1, but everything else is a 0. So this is our final outcome. And what we find is that the two tables are equivalent or are equal to each other. So that's enough. So that's enough to show that the two sides are logically equal to each other. Okay, so what I would invite you to do as another class exercise here is try to show that these two expressions are logically equal, but not using a truth table, but using algebra. Okay, so see if you can try to do this. These two expressions, try to show that they are logically equal by using algebra instead of a truth table. Okay, so I'm going to stop the recording here and I will see you in the next video.